Hello there, Mr. Sutton here with this lesson on the alternating series error bound. In this one, as the title suggests, we will be finding error bounds for alternating series, whatever all that means. We'll go into it in a minute. Now that you've been approximating for a while with finite polynomials, we're going to ask why. Why do we usually use finite Taylor polynomials to evaluate functions instead of an infinite Taylor series? And then what's the trade-off? Pause the video and contemplate this. Alright, so we're using these finite polynomials because it's easier. It's easier to add a finite number of terms than an infinite one. But there's a trade-off, and that's that we lose accuracy. There's some error. Let's talk a little bit more about this error. So it's the general setup when you use a polynomial. You had your true function value, which was the original infinite series, but then you actually just chop that off somewhere to create a finite polynomial that you plugged something into to get an answer that was, well, close enough, hopefully. But you were leaving out all those remaining terms that you didn't bother adding in. How many remaining terms were there? There was an infinite number of them. And just to express this a little bit more symbolically, our true function f of x we could write is our polynomial p sub n of x plus these remaining terms r sub n of x. So if we know the polynomial and the remaining terms, adding all that together would give us the true function value. But we don't know all those remaining terms, so we get some error. Let's talk about the error now. I'll call this definition error 1.0. Error 1.0 definition, this is just asking how far off is our polynomial approximation from the true function value. What is the absolute difference, subtraction, between that true value and our approximation? And just to write this symbolically, this is the absolute value of f of x minus p sub n of x. So we see this kind of expression, and this is talking about error. Of course, knowing this expression doesn't really help us find error because you would need to know the true function value in this setup. But if we already knew that, why did we bother approximating in the first place? So this brings me to definition 2.0 for error. And to get this definition, I'm taking a look at this expression, and I'm going to create that expression in this equation I wrote up here. F of x minus p sub n of x, if I wrote it from here, that would just be equal to this r sub n of x that I didn't bother subtracting. Well, what was this r sub n of x again? This was just all those remaining terms. So it seems that this error, another way of thinking about it is, this is actually just the sum, the positive sum, of those infinite remaining terms you didn't bother adding in for your approximation, the absolute value of r sub n of x. We'll talk a little bit more about this now. Knowing that the error is the sum of the remaining terms actually doesn't help a whole lot because there's still an infinite number of them. Because the error is an infinite series, we usually can't find its exact value. So instead, we settle for something else called the error bound, which is the maximum possible error, the maximum possible sum of those remaining terms. This is also pretty tough to find because, again, you have an infinite number of them. So we're going to use a special kind of series to demonstrate this today called the alternating series. The alternating series is just any series whose terms alternate between positive and negative. For example, this series right here. Pause the video and write out the first few terms of this series to see it in action. All right, so our first n value is 1. That gives us positive 1 over 1 for the first term. Next, for n equals 2, we've got negative 1 over 2. Then our next term is positive 1 over 3, negative 1 over 4, and so on and so forth. So to see how we could try to approximate the maximum possible error of a series, let's say that we try approximating this thing by stopping at the first two terms. So we're approximating with 1 minus 1/2, and hopefully that's close enough for the value of the whole series. But that means we have some error, right? So what's the biggest possible error if we just stop with these first two terms? The error, again, that's all the terms that you did not add in. So we've got the 1/3 minus the 1/4, plus, I'll be generous here, let's do a 1/5 as well. So what's the maximum possible value of all of this? Well, if we think about this for a moment, we start with 1/3, and then our absolute value gets smaller when we subtract 1/4. And if we add 1/5, we get a little bit closer to that 1/3 we started with, but we don't undo this whole negative 1/4. And then we subtract 1/6, that takes us further away. So if you keep adding and subtracting these successively smaller numbers, you're never going to get back to this first value. which means this 1/3 was as good as it was going to get. This whole thing has then to be less than 1/3. And if we started a little bit further down the line, let's say we started at 1/5 and start adding and subtracting, 1/5 is going to be as good as it gets. The first term in your error is always the biggest term because you're adding and subtracting smaller numbers. So this leads us into the alternating series error bound, officially stated here, which says if you have a series that alternates, like this one does, and you're decreasing in absolute value to 0, so your terms are getting smaller and smaller in absolute value as you go, then your error is just going to be less than the absolute value of the next term in that series, which in this case was 1/3, but really it's just the next term of whatever series you've got depending on where you stop adding terms. So in general, we can say error is going to be less than absolute value of a of n sub 1, the next term in any series that alternates like this. To see error bound in action, let's try this example. So let's say we evaluate a function using this series here. If the function value is approximated with only the first 74 terms of this series, what's the error bound to the nearest thousandth? All right, so we definitely have an alternating series here. So when we see that, we should try using the alternating series error bound. Now, before you use this, you need to first write out and verify the error bound. So writing it out here, again, that error bound says that if the terms alternate and decrease in absolute value to 0, then the error is less than the absolute value of the next term. So you should write this out if you're actually going to use it every time. But now, is it actually true? Do the terms alternate? Well, they do. And how do we know that? Because we have -1 to an exponent, so that's flipping us back and forth between negative and positive. Do these terms decrease in absolute value to 0? They do. The numerator is not really changing in size. The denominator, though, keeps growing as you plug in bigger and bigger n values. So we are decreasing to 0. So let's go ahead and use this now. So we need to figure out the next term, and then error is just going to be less than the absolute value of that. Pause the video and see if you can figure out an expression for the next term if we've already used the first 74 terms. All right, so if we've used 74, then the n value that would give us the next term would be 74 plus 1, or 75. So error is less than absolute value of something for now over 75. But now how about this stuff up top? Well, since we're already inside an absolute value, we don't need to write out -1 to some exponent, because that just changes the sign of the whole expression. So I'm just going to write a 1 up here. And now they wanted this to the nearest thousandth, so let's go ahead and calculate that on the calculator. So 1/75th on the calculator comes out to about 0.0133 if we take it out to 4 decimals, which we're going to do because they wanted nearest thousandth, 3 decimals. So should we round this off and say that the error is less than 0.013? Well, that wouldn't really be accurate because the error is definitely more than that. We've got some more decimals. Because you want to give an upper bound, you're always going to want to round up for error bound. If we're limited to only 3 decimals, then the best 3 decimal we can give here is 0.014, because whatever this comes out to, it's definitely less than that. In addition to figuring out error bound, sometimes a problem wants us to show that it's within a certain limit. On this one, we want to show that a 4th degree polynomial approximation of f of 1/2 for this function differs from the true value by less than 1 over 7,500. So we're going to need to find the error bound and then show that it's less than this number. So to start off with, let's write out our original series. Pause the video and do that to as many terms as you deem necessary. All right, so sine of x, I'm going to start with that. I'm just doing a Maclaurin approximation here. So that's going to be x minus x cubed over 3 factorial. And then do I need to go any further? Well, I know that when I multiply all of these by x in just a moment, I'm going to have an x to the 4th, which would give me my 4th degree polynomial. But if I want to use the error bound, I'm going to have the next term. So write one more term than the approximation actually requires so you can find that error bound. So I'm going to write out plus x to the 5th over 5 factorial. All right, now I'm going to do x times sine of x. That's x squared minus x to the 4th over 3 factorial plus x to the 6th over 5 factorial. Great. Now, the interesting thing about this problem is that they didn't actually ask us to find f of 1/2 approximated with these first 2 terms. They just want to know that the error bound is less than a certain amount. So we're actually just going to go straight to finding the error bound. So can we use alternating series error bound here? Well, these terms are definitely alternating, so that's an indication we could. Are they also decreasing in absolute value as we go? Here you have to be careful, because it's now the numerator in this series that keeps growing as you go further and further. But because you are plugging in 1/2, you actually have like 1 squared over 2, or 1 squared over 2 squared, 1 to the 4th over 2 to the 4th. You've actually got something that's growing in the denominator. So at the x value 1/2, our terms are alternating and decreasing in absolute value to 0. But always double check that. So again, that means our error is just less than the absolute value of the next term. What's the next term going to be on this one? Pause the video and see if you can write it. So if I'm plugging in 1/2, my next term, after I use the first 4 degrees of polynomial action, my next term is going to be 1/2 to the 6th over 5 factorial. And I could rewrite this as just 1 over 2 to the 6th times 5 factorial. Is this less than 1 over 7,500? Well, let's use the calculator to see what that denominator actually is. So 2 to the 6th times 5 factorial comes out to 7,680. So this is 1 over that number. And you might think, well, this is definitely less than 7,500 because the denominator is bigger, but we're not quite done. To get the credit on this problem, you need to show that this error bound is actually less than this value. So you need to actually explicitly write out less than 1 over 7,500, and then you're done. We're going to do one more problem. This one's a little bit of an oddball problem. Given this S series defined here, and P of k, a polynomial approximation of that series with k terms, we want the smallest k for which the alternating series error bound guarantees S minus P of k is less than 7 over 200. So let's take a moment to appreciate what they're asking here. We've got some series, we're approximating it, but we know we're going to have some error. We want to figure out how many terms we need to make the error less than a certain amount. All right, so to determine the number of terms needed for an error bound, first we need to actually write an expression for the error bound. So let's go ahead and do that. Now, is this an alternating series? It is. Are the terms getting smaller to 0 as we move on? They are. You have a denominator that's larger than the numerator, and your n values are just going up. So we can say that our terms alternate, decrease in absolute value to 0. This is, again, crucial to state this in the beginning. That allows us to say that the error is less than the absolute value of the next term. So let's go ahead and write that next term. Pause the video and see if you can do that, keeping in mind that we've already used up k terms. All right, so what's the next term then? It's going to be k plus 1 plus 3 over k plus 1 squared. So error is going to be less than the absolute value of that expression. We don't know what k value makes this thing come out to 7 over 200, but now we're going to find it by setting our error bound equal to that desired value. So I'm going to say this stuff equals 7 over 200, and I'm now going to try to solve this on the calculator. So in my calculator, I've written in y1 my error bound expression here. I didn't even bother simplifying it. In y2, I've got my desired error bound. I'm just going to see where these two things intersect. So let me do zoom 6 just to get a basic picture of what's going on. So there's my crazy error bound function. And I can't even see this other one because it's a very small number, very much less than 1, close to 0. So let me change my window. Obviously, we want positive numbers, so I'm going from 0 to something. Let's go from 0 to, I don't know, 100. And then zoom fit. I don't know how many terms this is going to take. It could take a bunch, though. So there's my error bound, and I can't even see the constant here. But let me just take a shot in the dark and do second, trace, intersect, and hope these things actually cross somewhere in this window. So enter, 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 and I lucked out. It turns out they intersect at about 30.3 and some change. If they didn't, I would just take my window out further and keep doing that until I got something that worked, or use a table to see where they match up. Anywho, we saw that this is about 30.3091. So what should I actually report for the k value? Because we're asking how many terms, and you can't have a decimal's worth of a term. Well, since more terms makes me more accurate, to make sure that I'm under this value, I have to take more terms than this decimal is giving me. So I'm going to want the 31st term, so 31 for my k value. So make no mistake, we are done talking about error bound for now. Till next time, Mr. Sutton signing off.